Okay, we're going to attempt to do this. Sorry if the recording is shaky. So we're going to start talking about probability, and the first thing we're going to talk about are sample spaces. So basic concepts of probability. We talk about probability all the time. Like what are the odds of something? So this asks, would you feel safer if you flew across the United States on a commercial airline or if you drove? How much greater is the risk of one-way travel to the other? So we talk about the odds of dying in an airplane versus dying in or not dying especially. It says if you feel safer, okay, which is safer, an airplane or driving, okay? So we talk about the odds of safety, okay? So the probability is the chance of an event occurring. A probability experiment is the chance the process leads to well-defined results called outcomes, okay? Outcomes would be like flipping a coin, rolling a 6 or rolling a 2 or something like that, okay? The outcome is the result of a single trial of a probability experiment, and the sample space is the set of all possible outcomes, okay? So a couple of things we have for experiments, we have tossing a coin, and your space would be heads or tails, rolling a die, 1 through 6, that would be a regular die. Answering a true or false question, the options are true or false. Tossing 2 coins, we'd have head, head, tail, tail, head, tail, or tail, head. And the order matters here, okay? All right, so this first one, we are finding the sample spaces for rolling 2 dice, okay? And it's, here would be die 2, and here is die 1. So you could roll a 1 first and a 1 second. A 1 first, 2 second, 1 3, 1 4. Okay, we're gonna go through here. And we have all the different rolls of a dice. So you could roll a 2 first and a 1 second. 2 3, 2 4, 2 5, 2 6, 3 1, 3 2. Oops. 3 3, 3 4, 3 5, 3 6, 4 1, 4 2. This is a little bit tedious. 4 3, 4 4. This will help us though as we are going along here. 4 5, 4 6, 5 1, 5 2, 5 3, 5 4, 5 5, 5 6, and then the last one we do our 6s first. 6 1, 6 2, 6 3, 6 4, 6 5. Thank goodness we get to stop at 6 6. Okay, so here are our total outcomes, and there would be 36 of them. Okay, 6 times 6. All right, so that is our sample space for rolling 2 dice. Okay. All right, coming here, so this one's already listed out for you. So drawing 1 card from an ordinary deck. Now, ordinary deck is going to have no jacks, or not no jacks, no jokers. Okay, there are 52 cards. There are 3 face cards. So face cards have faces, jack, queen, and king. We have red hearts, red diamonds. Okay, so there'd be 13 here and 13 here, so 26 reds. And then we have black spades and black clubs, 13 here and 13 here. So that would be 26 black cards and 52 total. 52 total. All right. So this one, if we're going to draw out the gender of a family, if the family has 3 children. So we start with a tree diagram. Okay. So we'll start here. The 2 options we have are boy and girl. Okay, so this would be for the first child. Okay. The second option, so if they have a boy first, they could have a boy second or a girl second for their second child. But they could also have a girl first and then boy first, or boy second or girl second. And then each one of those for the third child, you can go boy, girl, boy, girl, boy, girl, boy, girl. Okay, so this would be all of our possible outcomes. So you could go boy first, then girl, then boy, boy, girl, 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 boy, girl, girl, boy, boy. My particular family, because I have 3 kids, we went boy, boy, girl. So that would be my route right here. Okay. All right, and this is called a tree diagram. You can draw them sideways like this, or you can draw them up and down, kind of like a number tree this way. Okay. All right, probability rules. The probability of an event is a number, either a fraction or a decimal, between and including 0 and 1. This is denoted by, so it could be expressed as a fraction, a decimal, or sometimes a percent. Okay, so the sum of the probabilities of all the outcomes in a sample space is 1. So this is for a dice, okay? The outcome, you have 1. The probability of rolling a 1 is a 1 in 6 chance. A 2, that's a 1 in 6 chance. 3, 4, 5. And this is assuming it's not a weighted dice. Okay, the sum would be adding all of these up, and this should add up to 1. Okay, so this is 1, 6 plus 1, 6, 1, 6, 1, 6. Okay, that will all add up to 6 over 6, which is 1. Okay, if an event cannot occur, that means the event contains no numbers in the sample space, its probability is 0. So for example, rolling a 7, that would be an impossibility, right? Okay, if an event is certain, then the probability is 1. So if, let's see, if you have, I'm not good at thinking of these on the spot. So the probability of me drinking a Dr. Pepper on a day that I need a Dr. Pepper is a probability of 1. It's going to happen. Okay, that's a bad example, but my brain is not working. It's late and I need to sleep. Okay, I think these might have gotten out of order. Oh shoot, but we'll figure it out. Okay, here is example 2. All right, so I think this was supposed to come after this one. Find the sample space for this. Let's keep going with this one, okay? What is the probability? Hang on, I'm gonna pause. Okay, back on track. What is the probability of getting a 9 when a single die is rolled? Okay, well, is that even possible if we're doing a regular 6-sided die? No. So the probability of 9 is going to be 0. Like, that doesn't happen because the 9 does not occur on our dice, right? We only have 1 through 6, okay? What's the probability of getting a number less than 7 when a single die is rolled? The probability n is less than 7, okay? Well, all of the numbers are less than 7, so that is certain. That means that will happen. So the probability of that will be 1. Now, all of your probabilities are going to be within 0 and 1, okay? Anything over that, you can't actually have more than 100% when it comes to probability. It's either it will not happen at all, it's impossible, or it is certain, okay? And then everything will be in between those two numbers. So if you get a number that is like 1.7 or 1.2, anything above that, you've done something wrong. If you're getting a number that is less than 0, then you've also done something wrong. Okay, so the next one, let's talk about a simple event. A simple event has one outcome. So for example, getting a 6 when a die is rolled. Okay, that happens once, that's it. Okay, a compound event has 2 or more outcomes. So like getting an odd when a die is rolled. You can get 1, 3, or 5. Those are odds, right? Okay, So we have three interpretations of probability. They are classical probability, empirical or relative frequency probability, and subjective probability. So let's talk about classical or theoretical probability. This uses sample spaces to determine the numerical probability that an event will happen. If an event has n different events that are equally likely, then, let's see, I've lost my notes. Hold, please. Of course, they're out of order. Okay, if an event has n different events that are equally likely, then the probability of the event equals the number of ways E can occur over the number of different simple events. Okay, so this would be the total outcomes in the sample space right here. Total outcomes in the sample space. Okay, so we are going to calculate some of the probabilities of doing these here. Okay, so one card is randomly selected from an ordinary deck. So if you want to reference back to here, okay, that's what I'm going to look at. So it says, find the probability of getting a black 6. Okay, so probability of black 6. Okay, how many black 6s are in the sample space? We have the 6 of spades and the 6 of clubs. So that would be 2 out of how many total cards do we have? It'd be 52 in a standard deck. Okay. Now, this technically is correct, but we are going to simplify this. This would be 1 out of 26. Okay. Which is approximately 0.038. Okay. You can write it either of these ways. Okay, this would be one answer. This would be one answer. All right. What is the probability of getting a jack and a spade? Okay, and remember, we only have one card. Okay, so probability of jack and a spade. Okay, that would be the jack of spades, right? How many jack of spades do we have? Okay, that would be just this 1 out of 52. All right, so that'd be 1 out of 52. We can't simplify that, but the answer to that would be 0.019. Okay, so this would be in fraction form. This would be in decimal form. All right, find the probability of one card of getting a diamond or a heart. So probability of a diamond. Notice on this one it says or instead of and. Diamond or a heart. Okay. Now, can you get both a diamond and a heart? No, it doesn't exist, right? So you'd either get a diamond. So how many diamonds do we have? Be 13. Or a heart. How many hearts do we have? That would be 13 as well. So diamond or heart, that would be 26 options out of 52 total. Okay, so if we simplify that, that's going to be 1/2 or 0.5. Okay. So there's a 50-50 chance of you drawing a card and getting a diamond or a heart. Okay, there's only a 1 in 52 chance of you drawing one card and getting a jack and a spade. Okay, so here's example 4. A family has 3 children. find the probability that exactly 2 of the 3 children are boys. Okay, so let's go back to our options here. So the total number we'd have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 possibilities. 2 times 2 times 2. So 8 total outcomes in this 3 children family. Okay. Outcomes with an S. Okay. All right. So the family has 3 children. Find the probability that exactly 2 of the 3 children are boys. So probability of exactly 2 boys. Okay. So if we look at our tree, let's count the ones that have exactly 2 boys. That one does not. There's 1. And then we're going to have 2. Let's see. Is that it? Yeah, everything else is good. Oh, wait. Here's 3. So we've got boy, boy, girl. Boy, girl, boy. There's 2. Girl, boy, boy. There's 3. And everywhere else does not have any more, or it doesn't have exactly 2 boys. So that would be 3 total out of the 8 possibilities. Okay, so there's a 3 in 8 chance that you get exactly 2 boys. Okay, if we simplify this, this is going to simplify to 0.375. Okay, that's the probability of having exactly 2 boys. What's the probability that at least 1 child is a girl? All right, so the way we write this is P is at least 1 girl. Okay, that means we can have more than 1, but we have to have at least 1. Okay, so that one's out. We have 1, 2, 3, 4, 5, 6, 7. So 7 possibilities out of this have at least 1 girl. Okay, basically the only one that wouldn't work here is the one with all 3 boys. Okay, so that would be 7 out of the 8 total possibilities. All right, and if we put that in our calculator, that ends up being 0.875. Pretty high probability that you're going to get at least 1 girl. Okay. All right, example 5. If 2 dice are rolled at one time, find the probability of getting these results. So this will be on the next page. Okay. Here's what we are looking at. And we have already written out our sample space right here, the 2 dice. Okay, and let me get my notes to the right spot. Right. Good grief, they're all out of order. Okay. All right, we're rolling 2 dice. What is the probability that the sum is less than 9? All right, less than 9. So this one, we had a total of 36 outcomes. Okay, so the bottom of our fraction over here is going to be over 36. All right, let's look at the ones that sum up to 9. So this would be 2, 3, 4, 5, 6, 7. Okay, this would be 3, 4, 5, 6, 7, 8. So all of those. 4, 5, 6, 7, 8, 9. So that one would be out. Yep, because we say less than 9. Okay, so not here. We've got these first 2 lines, then up to here. We've got 5, 6, 7, 8. So not here. We've got 6, 7, 8. Not here. 7, 8. Not here. So basically, we're making this line right here. And this corner is not included because those would be 9 or higher. So let's count those up. We have 6, 12, 12 plus 5 is 17, 17 plus 4 is, oh my gosh, 21, 21 plus 3 is 24, 25, 26. So we have 26 numbers that would add up to, whoops, there we go, 26 of our dice that we roll out of 36. And those are the ones that are less than 9. So probability that we have some less than 9. I ran out of room. Equals. Okay, so we have 26 out of 36. That's going to simplify to 13 out of 18. And that, if we plug that into a calculator, it gives us approximately 0.722. Sorry, my camera skills are rough. I'm holding my phone with one hand and writing with the other one. Okay, again, we're rolling 2 dice. We want to find a sum of 9 or 10. So let's write that down. Probability sum of 9 or 10. Okay, so go back to our sample space. We knew the 9s were like right here-ish. So this would be 9, 9, 9, and 9. So there's 4 of them there. 10, 10, 10. There's 3 of them there. And then these are higher. These are 11 and 12. So these 3 and these 4. So that'd be 7. 7 of these add to either 9 or 10 out of the 36 that we had total. Okay, so 7 out of 36. That would simplify, or that's the decimal, to 0.194. So you can write it both ways. Okay. All right, so this one asks, what is the probability of rolling doubles? All right, let's see how many doubles we have. Okay, 1, 2, 3, 4, 5, 6. So we have 6 out of 36. Is it very likely? Same as 1 out of 6. And that is 0.167. Oh, so sorry to whoever is having to watch this because everyone just went 6, 7. Right? All right, so not very likely that you're going to roll doubles. It does happen though. Okay, so all of these are under the theoretical or classical probability. This is if you run it and it's like, hey, this is what should happen. Okay. Empirical probability or relative probability relies on actual experience. So this is like, okay, this is how it should turn out, but how often do you like, oh, I actually got doubles a few times in a row, and you defy this. Okay, so that's going to be our relative frequency or our empirical probability is when we actually run this situation. Let me get my notes to the right place. Okay, so this one, the probability of the event equals the number of times E occurred, the event occurred, out of the number of times the procedure was repeated. Okay, so say I did 20 times that I rolled the dice, and then I actually wrote down what happened. Okay, this is going to change the outcome. All right, here we go. New probabilities. In a sample of 50 people, 21 had type O blood, 22 had type A, 5 had type B, and 2 had type AB blood. Set up a frequency distribution and find the following probabilities. Okay, so A blood was 22, B blood was 5, AB was 2, and O was 21. Okay, now this is not how the theoretical probability would be. Type O blood is pretty rare. Okay. So we're going to total this up. 22 plus, oh, we said we had 50. So total would be 50. Okay. So this is going to be the denominator for our probabilities. So what is the probability that somebody has type O blood? Okay. How many people had type O? That's 21 out of 50. So if we simplify that, that is going to be 0.42. Okay, either one of those. This one, the probability that person has type A or type B. Okay, type A or type B. So type A was 22 and type B was 25. So that total would be 27 out of 50. Okay, and that simplifies to 0.54, a little over half. Okay, a person has neither type A nor type O. Okay, so that means the A's are out and the O's are out. How many are left over? So that'd be B's and AB's. So that would be a total of 7 out of 50. That simplifies to 0.14. And then a person does not have type AB. Okay, there were only 2 people that had type AB, so the rest of them would fit here. That would be 48 out of 50. Pretty high probability for our situation. That is 0.96. Okay. All right, so let's look at this one. A recent survey found the following distribution. Find the probabilities for a person selected at random. Okay, so this is how many hours people sleep at night. Less than 6, 6, 7, 8, or more than 8 hours, and they totaled them up for you. So we had a total of 100 people that they surveyed, and here are the answers we have. All right. What's the probability that a person sleeps 8 hours at night? Okay, so if we go over here, find out we have 28 people out of 100. 28 out of 100, that simplifies to 0.28. What's the probability that a person sleeps fewer than 7 hours? So notice they didn't say equal to. So fewer than 7, that would be 6 or less than 6. So if we add those two together, we have 26 plus 12, we're going to end up with 38 people out of the 100. So that's going to be 0.38 as our probability. The person that sleeps at most 8 hours a night. So at most means 8 and less. Okay, so that would be 12 plus 26 plus 30 plus 28. So if we add all of those up, basically it's everybody but the more than. So 100 minus 4, that makes 96 out of 100. So that's a pretty high probability that they sleep at most 8 hours a night. Okay. Next one, let's look at the college debt. This gives us a frequency distribution. So this shows the information of the amount of debt students who graduated from college incur for a specific year. Okay, so 1 to 5,000, 501 to 20,000, 2001 to 50,000, and then more than 50,000 right here. Okay, and then these percentages should add up to 100%. Okay, if a person who graduates has some debt, find the probability that the debt is more than 20,000. Okay, so more than 20,000, that would be this one and this one. So we'd say 19% plus 14%, that equals 33%. Okay. So 33% of our sample has more than $20,000 in debt. Okay. What percentage of the people that graduate with debt have between $1 and $20,000? So we have 27% here and 40,000, or no, 40% here. 27% plus 40%. that equals 67%. Oh man, I'm in pain already. Okay, so let's talk about the law of large numbers. This says that when a probability experiment is repeated a large number of times, the experiment, or the relative frequency probability of the outcome, will approach its theoretical probability. So the more and more you run this, the closer it's going to get to its actual theoretical probability, okay? If we only run this a few times, so like if we were rolling dice and stuff and we only did it 10 times, it's gonna be way skewed. But say we roll double dice 500 times, it's gonna get closer and closer and closer to the probabilities that we have from this table, okay? All right, subjective probability. Let me get to my, here we go. So subjective probability uses an educated guess or an estimate, okay? For example, a doctor might say that based on her diagnosis, there's a 30% chance that the patient will need an operation, okay? This is coming from data collected before. It says like, okay, well, people in your case, you know, it has been that 30% have to get the operation after this kind of an injury, okay? And that's taken off of data, and so it's a best guess, okay? All right, let's talk about the complement, okay? This is not like, oh, you look nice today. This is complement, not compliment. Okay, the complement of an event is a set of outcomes in the sample space that are not included. Okay, the complement is denoted by the complement of, sorry, this isn't written in here. E is denoted by E bar. Okay, so say that this is our sample space here. All right. Whatever it is, okay? And here's the event happening, okay? Everything in here is the event. Everything outside of it would be E bar, or the complement. So for example, say we're rolling 2 dice, okay? And we've got all of our, or say we're even just rolling 1 dice, right? And we've got our options here, 1 through 6, right? The event could be rolling an odd, okay? So what would occur in here would be 1, 3, and 5. Okay, the complement would be 2, 4, and 6. Okay, that would be what is outside of it. Say a different event. Say it's 5 or greater. You roll a 5 or higher. Okay, so 5 and 6 would be in here, and then 1, 2, 3, and 4 would be the complement. Okay, so let's find the complement of each event. Okay, so selecting a month that has 30 days. Okay, what would be the complement of this? Now, there's a couple of things to note here. Okay, the wording's a little goofy here because if we're going to say selecting a month that has exactly 30 days, that changes it because like February does not have 30 days, but or like basically all of the months have 30 days except for February. But if we want exactly 30 days, that would exclude the complement would be selecting a month with exactly 28 or 31 days. We're going to ignore leap year because it doesn't happen enough. Okay. All right. So finding the complement, rolling 2 dice and getting a number whose sum is 7. Okay. The complement would be pretty much any other option that we had. So rolling 2 dice and getting a sum of, okay, the lowest we can get is 2, 3, 4, 5, 6, 8, 9, 10, 11, or 12. Now that seems kind of excessive, but those are our other options. We can't roll 2 dice and get a sum of 1, okay? And we can only go up to 12. All right, selecting a letter in the alphabet, excluding Y, that is a vowel. What would the complement be? Selecting a consonant, right? Okay. What is the complement of getting 2 heads when 2 coins are tossed? Okay. What are the other options we can get? Getting a tails, a tails, heads, or a heads, tails when 2 coins are tossed. All right. Okay. So rules for complementary events. I'll go up here. We have a couple of things. So we have, what is the probability of the complement? So E bar. That would be 1 minus the probability of the event, right? Because 1 would be all of the probabilities. So it's like 100%, right? So if we do 1 minus, and then this is going to be between 0 and 1, 1 minus the probability of the event happening will give us the complement. Or we can have the probability of the event equals 1 minus the complement. Okay. And the third one is the probability of the event plus the probability of the complement has to equal 1. Okay. These are the 3 options. Okay. And depending on your problem, what it looks like, is kind of how you're going to decide which one of these works the best. Okay, so let's look at example 8. All right, in a study, it was found that 24% of people who were victims of a violent crime were ages 20 to 24. If a person is selected at random, find the probability that the person is younger than 24 or older, or younger than 20 or older than 24. Okay, so let's write this down. Probability they're younger than 20 or older than 24. Okay, so this is how we would note this. And sometimes this is kind of long, what we have to write, but it should describe what we're looking at. Okay, so we were given that 24% were between 20 and 24. So the complement would be everything outside of that, which is what we're looking for. So we're going to use this one here, 1 minus the event. 1 minus 24%, or we're going to change this to 0.24. Okay, and that's going to equal 0.76 or 76%. Okay. All right, last example. Let's classify these as an example of classical probability, empirical probability, or subjective probability. Okay. Remember, classical is theoretical. Okay. Empirical, that's like our experiment. Or subjective is the our educated guess. All right. The probability the person will watch the 6 o'clock evening news is 0.15%, or 0.15. Okay, so this one is going to be empirical. Okay, this is that you actually took a sampling and you found that 15% of people actually watch the news at 6. All right, this one. What is the probability of getting a royal flush when 5 cards are selected at random? And this is 1 over. I don't know why this didn't write in here. Hopefully between the time I recorded this and your notes, I will have this fixed because this should be written in there for you, okay? So the probability of getting a royal flush when 5 cards are selected at random is 1 out of 649,740, okay? That is going to be classical probability, okay? That is taking your odds, like your different cards and like how many royal flushes can you get. You get 1, and then I'll teach you how to calculate this later on, but this is just given to you. This is classical. We didn't actually run it of, you know, dealing out a royal flush, okay? All right, this one. A sports writer says that there's a 70% probability that the Pirates will win the pennant this next year. Okay, is there any way to actually predict that? No. So this one is going to be the subjective. Okay, based on like how they've been playing and like odds that way, this would be a subjective probability. Okay, hopefully that makes sense. And we will get to the rest of this, or no, this is all the notes, but we will go over this a little bit more when I get back. Okay, bye.